Let's talk business, right? So Dylan Beattie is a consultant, software developer, and international keynote speaker. Dylan is the creator of the Rockstar programming language and the director of Ursatile. I think I said it right. There is no such thing as a plain text with a very warm round of applause, just also to give you some energy, and I promise I'm not going to make you participate in the session. Let's welcome Dylan to the stage.
Good afternoon. How's everybody doing out there? So my name is Dylan Beattie, and my PowerPoint, there we go. The PowerPoint clicker is working. That's always a good start. I'm a developer. I've been building websites and database systems since they invented the web, basically. I'm a Microsoft MVP. I run a .NET user group in London, where I'm based. And yes, I invented my own programming language as a joke. The language is called Rockstar. And Rockstar programs look like heavy metal songs. So even if your code doesn't work, you can still plug your guitar in and sing your program. And Rockstar started out as a joke, and now it's a joke with a reference implementation and a test suite. And I'm the project manager of an open source joke, which is not how I thought my life was going to end up, but here we are. Now, I love giving this talk because every time, this talk has been around for a couple of years now, and every time I get to go somewhere and present this stuff, I get to learn a lot as well because I do some research, I talk to locals, I find out what do they do here that's a little bit different to the rest of the world. And sometimes I do this at conferences and they go and they put the presentation on YouTube. And the people on YouTube, they have opinions, and they really like to leave little comments going, of course there's such a thing as plain text. Plain text is 850 words later result in a long final destination. I don't know what this guy is smoking that day, but also I get people on YouTube telling me stuff that I had no idea. They're like, I used to work in an office next to the people who invented ASCII, and I'm like, tell me about this. This is fantastic. So this talk is just all these little bits and pieces of interesting stuff that I've pulled together from 5 years of online and in-person going around and talking to people and going, hey, what's it in your country when text files don't work? What happens? And working through it. And yeah, is there such a thing as plain text? Because we're all like, just send me a plain text file, because that means I'll be able to open it. And what generally, if you go around the world and ask a lot of people, when they say plain text, what they mean is, I want 7-bit ASCII so I can open it in Windows Notepad and it'll look the same as it's supposed to. And ASCII is one of those things, we don't think about it as developers. It's always been there. Like, there might be 1 or 2 people in this room who were alive when ASCII was invented, but most of us, we were born in a world where ASCII exists and we just have to deal with it. But ASCII's actually really clever. The thing about ASCII is it was designed on purpose to work on these. It was designed to work on mechanical computers and teleprinters. It was not designed to work with screens. It was designed to work when a computer was a typewriter with a memory. And so a bunch of folks sit down in the United States in the 1960s, and they're like, all right, we need to design an encoding system so we can put text in the computer. And I actually think that given the constraints, they did a remarkably good job. It's just a lot of those constraints don't apply anymore, so we've forgotten what they were. Because you take the top block, like the basic first block of ASCII, there's a bunch of characters in here. We've got the 0 null character at the end, and C developers still use that. And then we've got a bunch of things here. Now, the start of heading, if you were on your mechanical teleprinter and you wanted to send start of heading, it had a key on it called Control. And you'd press Control, and you'd press A, and it would send a start of heading, like, okay. And a start of text. Now, these ones we don't use anymore. But end of text meant stop. It meant stop printing, something's gone wrong. That's Control-C. And that one, who's used Control-C this week? Because I know, yeah. Because when you're like, oh, I forgot to check the loop, ding, ding, Control-C, 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 stop the program. And so then we've got end of transmission, we've got inquiry and acknowledgement, we've got bell, number 7 there. You can actually echo that on Windows, and it goes, ta-da, and it plays a little sound effect. And then we get this whole block of tab characters for doing indentation, line feeds, vertical feed, form feed, carriage return. These were all to control mechanical bits of the teleprinter. Because a teleprinter was based on something called a carriage. So the carriage would move across the page, and it would print stuff. And then when you got to the end, you had to return the carriage to the other side. So that's a carriage return. And then you'd need to feed the next line of the paper through. Now, teleprinters were kind of dumb. They couldn't do fonts, they couldn't do graphics. What they could do is you could print a line, and then you could send a carriage return, and then you could print the next line again. And it would come out kind of bold, because it didn't line up exactly. And so a carriage return by itself was useful. But a line feed by itself, yeah, not so much. You don't need, because then you're going to fall off the end of the page. You need to return the carriage. And so we ended up with this weird set of historical quirks, where what's happened is that most systems based on Linux and Mac OS today, they just say, yeah, new line. You want to end a line? New line. Because those systems, Linux evolved out of Unix, and Unix evolved out of Multics, and Multics was one of the first operating systems ever that had the idea of a device driver. It meant you had a little piece of code between your operating system and your hardware that could just put the carriage return in for you because it knew you were always going to need one. And so the text file just had to have the new line, and the machine would do the right thing. Windows, Windows, like you need a carriage return. Now, I don't run Windows on a mechanical teleprinter, but Windows 11 out of Windows 10 out of Windows 8, they skipped Windows 9 because everyone would think it was like Windows 95, all the way back to MS-DOS, which evolved out of CP/M, which evolved out of a system called Minix, which was designed to run on really, really cheap hardware and didn't have device drivers. And so if you wanted to print carriage return and then go to the next line, you had to send a carriage return new line. And 50, 60 years later, here we are, still opening text files and going, my coworker's on Linux, I'm on Windows, and we can't read each other's plain text. Now, the next block, there's some really neat ideas in the next block here. One of the things that computers have to do a lot is they turn digits that humans can read into numbers that computers can use to do arithmetic. And the way you do that in ASCII is you just ignore half of it. If you ignore the big 4 bits, the other 4 bits, that is the binary representation of the value of that digit. And this is blisteringly fast. Even on the kind of computers they had in the 1960s, just ignore the top half. There you go. Do the arithmetic, stick the top half back on, and there you go. You've got your digits you can print out so the human beings can look at it. The alphanumeric block. Now, I remember the first time I became aware of ASCII, one of the things I didn't understand is why did they pick these numbers? Why would they pick 65 for the uppercase A in the Latin alphabet, and 97? Why did they leave this little gap here with the punctuation in it? And the reason they did that is if you look at the bitwise encoding of upper and lowercase strings, they only vary by 1 bit. So if you switch that bit off, you can do case-insensitive sorting, case-insensitive collation. And again, it's 1 bit. Ignoring it is cheap and it's easy, even on relatively low-powered computers. And then right at the end, we got a whole bunch of punctuation. One of the decisions that ASCII had to make is, what punctuation are we going to include? Because we've only got 128 characters. We got all the control characters. We don't have space for all of it. And anybody who's worked in print or typography, we've got an M dash, and we got an N dash, and we got a hyphen, we got a minus sign. They're all different in publishing, but ASCII went, no, just 1. You can live with 1, that's fine. And then right at the end of the block, they've got the ASCII delete character, which is 111111 in 7-bit ASCII. You know why? Because you can't fill in the holes on a tape. The only way to erase data from a tape is to punch out all the other holes, so you can't read what was on it before. And so this solves all the problems they have, and the United States turns around and it's like, hey, all 127 characters, all you're ever going to need. And the rest of the world goes, we can't work with this. Now, there are some countries and alphabets and cultures for whom ASCII just, no, if you grew up with Japanese or Korean or Hebrew, ASCII didn't even help you a little bit. But there's also a lot of places where ASCII was almost good enough. I grew up in Zimbabwe, which is a country where I grew up speaking English and using dollars and cents as the currency. And so for me, ASCII did everything I needed to do until I was 10 years old. It's when my family moved to the UK. And in the UK, we have this currency symbol. We have the pound sterling sign. And that didn't make the cut, because it wasn't important enough to Americans in 1965 that they included it in ASCII. And so when I'm about 11 years old, I've got my 286 PC, and I've got my Epson dot matrix printer, and I'm trying to print out my homework, and when I go to print it, I get this. And I'm like, what's going on? Now, what's happening here is a whole bunch of people around the world, people like, the British, they had this symbol. Most of the rest of ASCII was okay. Other places, Western Europe, they have some accented characters. Scandinavia has some accented characters. They all look at ASCII and they're like, well, hang on. The Americans only used 7 bits. They only used the bottom half of the character set. Can we use this bit? And nobody was regulating this stuff internationally because they couldn't. And so everyone went, awesome, we're going to use the top half of ASCII to solve our problems that we have in our country. And they invented what became known as code pages. So if you ever come across a code page, that's what a code page is. It's a set of rules that says right here, today, if you open this document in this application on this computer, this is what the top half of the 8-bit ASCII character set looks like. Now, one of the most infamous code pages was a code page number 437 that shipped. This was the default code page on the IBM PC and became the default code page for MS-DOS in English-speaking countries. And they did some pretty neat things with this. So the top half of this, it included all the accented characters necessary for Scandinavia, Northern Europe, Western Europe, Germany, those kinds of countries. It's got all the box drawing characters, so you could do menus and build little interactive GUIs. It's got half of the Greek alphabet. So I don't know why it has half. They didn't care about Greek. You couldn't use code page 437 to write email in Greek, but you could use it to write physics. So they took the Greek characters that you get in kind of up to a high school level maths and physics textbook, and they put those in the code page. And then somebody at IBM is like, this is not a teleprinter. We probably don't need all the control characters. Why don't we use the top 32 bits to do fun things like smiley faces and playing cards? And if you've ever seen an IBM PC crash really hard, it crashes with a screen full of gibberish that's little smiley faces and playing cards. And that's because it's taking all of these very low-numbered machine code instructions and it's trying to print them using the default code page, and that's what you're getting coming out on your screen. Now, there was a convention for writing the Cyrillic alphabet, Russian, Ukrainian, Bulgarian, a couple of other languages, a convention for using the Cyrillic alphabet, a code page for that. But it didn't work very well. And the reason it didn't work is that a lot of applications assumed that text files only used 7 bits. It's a famous word processor. It's called WordStar. It used to use the 8th bit to indicate, have you done a spell check on this word, yes or no? And so your text would get mangled. So if you said hello to somebody in Russian, you say Privyet, and you turn that using the international code page, you get this bunch of bits, then WordStar comes along, spell checks it, your 8th bit falls off, you turn it back into text, and you get, nah, you can't make any sense of that. And so a bunch of people went, right, the official standard doesn't work. We're going to create our own ASCII extension. We're going to create the Kod Obnema Informacja 8-bit, KOI8. And what this did, which I just think is really neat, is it didn't use alphabetical order. It used sound alike. So you'd take Privyet, and you'd transcribe that. You'd lose your 8th bit. You'd turn that back into ASCII, and you'd get that come out the other side. And you can see it's been mangled, because like the uppercase has gone to lowercase, so everything's been reversed, but you can read it. You're like, Privyet, okay, I think I can see what they're getting at. Now, I gave a version of this talk a couple of years ago. Somebody comes up to me afterwards and said, do you know about the Harry Potter book? I'm like, no. What's the story? And they sent me a link to this thing. I went down this wonderful rabbit hole. In about 2002, there's like an internet fan site when people used PHP forums to talk about things like Harry Potter. And there's a couple of people. One of them is in Paris, and the other one is in Moscow. And I've made up the names. We don't know the name of one of them because it's lost to history. But basically, this lady in France is saying, hey, do you want me to send you the new Harry Potter book? Because maybe you can't get it in Moscow yet. And get this email back, yeah, that would be amazing. We cannot get the new Harry Potter book here in Russia. Here is my address. It is in Russian alphabet, so please copy it carefully. And that's a street address of an apartment building in Moscow, which I am not going to attempt to read. Now, this gets sent to Claudette, who's running Microsoft Outlook on French language Windows. Comes out like that. And she goes, all right, I guess that's how they write addresses in Russia. And very, very carefully, now this is the same data. It's the same bytes, same underlying data stream. Nothing has got lost. It's just being interpreted differently. So Claudette takes it and very diligently copies it onto an envelope and puts it in the mail. And somebody in the Russian postal system looks at this and goes, da, and they fill in all the blanks. And the book gets delivered, and this ends up. Now, folks, I'd like you to get your phone out your pocket, and I want you to go onto Spotify, Google Play, whatever it is that you use to listen to music, because I want you to search for something. I want you to search for this word. You got it? Billy Joel. Live in Leningrad. 1987, Billy Joel and his band became some of the first Western artists to perform in Leningrad, St. Petersburg, Leningrad, the Soviet Union. And they recorded it, and it was released. And it was released as concert but the title of the album was spelt in Russian, in Cyrillic. And then this made it into a database. And at some point, like somebody working at the record company, they get this, and they're sitting there looking at their American keyboard, and they're like, K-O-H-U, I guess, E-P-T. So it became Kohuept, and it just went in like a stock management database. But then, of course, what happens is streaming comes along, and Spotify and Apple Music, and everyone are like, hey, Sony, do you have like a database of all your albums? And they're like, yeah, well, you can have this one that we use in the warehouse, and that just became the title of the album. And so the album is called Kohuept Live in Leningrad. It's not a word, it's a transcription error that's the title of a record. Now, any of you folks read Russian? Does that say anything? No, it's gibberish. It doesn't mean anything at all. But if you type this onto a Cyrillic language keyboard layout, these are the keys that you press. This is the pattern you make with your fingers. And if you type that same pattern on a British or an American keyboard layout, you type Taylor Swift. And Google knows about this, because if you go on Google and you forget to switch your keyboard layout from Cyrillic back to English, and you search for Taylor Swift, it's like, I know what you're looking for, I know you forgot to switch your keyboard layout, and I'm not going to give you a hard time about it. Now, this whole system of encoding and code pages and different character systems, it kind of worked for a while, but when we got the internet and the web and email, this is the list of code pages that exist on Wikipedia right now. And it's not even like we had to stand, like, if you wanted to send somebody a document written in Bulgarian, you had to know if they were using like an IBM mainframe or a PC or an Apple Mac or a PostScript system, because they had different ways of doing Bulgarian. We needed a better system. We needed a unified encoding system, and so the Unicode Consortium was born. And Unicode has a wonderful mission statement. They say our job is to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Now let's work backwards there. All computers and devices, if you want everyone in the world to use your thing, you've got to make it really good and you've got to make it completely free. And they did that, and it worked. And that's how come we can post emoji in Slack, and we can send each other text messages, and I can come here to Hungary, and my English phone works, and that's fine. All human languages, like not just the ones we're using today, they have ancient Egyptian hieroglyphics. They've got ancient Sumerian, because people doing archaeology, people doing historical research, they get to play Unicode as well. And so that means that each letter and symbol, that's the important part here. Now, this is where it gets really interesting. Now, I enjoy learning languages. I enjoy word games. And so when I got here yesterday, I went down to a Regiojatek, and I picked up a Hungarian language Scrabble set, because I figured that's a fun way to get to know the language a little bit. And I sat down. I was like, let's play a game of Hungarian language Scrabble. And what do you know? The first letters I pulled out the bag, Nemchak. Nemchak shirtishik hanem wishkitik. He doesn't drink beer, only drink beer, he also drinks whiskey. I'm like, it's amazing. That's a 7-letter word in Hungarian, right? It's not. Or it is, or it's not. No. Because that's how you spell it in Hungarian Scrabble. Now, I've never seen a Hungarian Scrabble set before. When I open it up, I'm like, what? This is not how Scrabble works in English. So I went on Wikipedia. I'm like, all right, let's fix this up. How many letters are there in the Hungarian alphabet? And it says here, it's based on the Latin, several added variations, 44 letters in the Hungarian alphabet. These 44. And my English brain is looking at that and going, I'm a little confused right now. And so I kind of went through, I'm like, okay, so 26 basic ASCII Latin alphabet characters. We got all of those. So those are the same as they're the ones that I grew up with. And then there's a bunch in here which are accented characters, which Unicode has said you get one code. That's one letter, says Unicode, and it gets one code point. Now there's an interesting one here, because the letter Z has a Unicode code point. Actually, it has 3, because it's got uppercase, it's got upper lowercase, and then it's got lower lowercase, which I think it's unique. It's one of the only letters that does this. So technically, Z has a Unicode code point for that letter. But if you look at a Hungarian keyboard layout, it's not there. So it doesn't get used, because you're not going to go and look it up. You're just going to, Z is on there, so you're going to type those two. So that one we're kind of not sure. Like, is it not? The rest are what are called digraphs, which is 2 letters that make 1 letter, or 2 characters that make 1 character. Apparently, Hungarian language teachers really struggle to get people like me to understand this concept. There's trigraph, which is the J. So the word jungle, like welcome to the jungle, the first letter of that word in Hungarian is 3 letters that make 1 letter. But then we've got QWXY. These I understand these don't occur in Hungarian unless you've got loanwords like whiskey. Because you've got to be able to have W, otherwise you can't order whiskey, but it's not a Hungarian word. It's a borrowed word. And so the Hungarian alphabet, 44 letters, 35 of them are on your keyboard, 41 of them are in the Scrabble set, Unicode, 36 of them are independent letters, except the Z doesn't get used like that. It lives off over here by itself. Now, how many of you looking at this and you're just going, yeah, it's fine? Yeah. See? Because it is fine. Because it's what you grew up with. This makes absolute perfect sense, not a problem whatsoever. But the kind of people who invented ASCII and did a lot of the pioneering work on email and the internet and word processing and Microsoft and all that kind of stuff, we didn't grow up with that. We grew up with this. Our brains can't cope with the different, because we're like, what do you mean it's a letter but it's not in Scrabble? How is that possible? And so this is why I find, language and text and encoding and stuff so fascinating, is because most people grow up with something that just makes sense to them because they've been learning it their entire life, and they don't notice the things about it that are unusual. And then you travel, or your company does an integration with somebody in another region, and you're like, whoa, I had no idea this could get so complicated. Let's meet some friends of mine. Francois Borda is an archaeologist from France, and Motley Crue is a rock band out of Los Angeles in the United States. And Francois has a little sadir here. The little C has a tail under his name. And the word archaeologist here, they've used a very old-fashioned convention, and they've mashed the A and the E together to make a thing called a ligature. It's called a ligature. And Motley Crue, they put umlauts, diareses, on the O and the U because they think it looks cool. It's a heavy metal umlaut. And the first time Motley Crue went to Germany, the audience is chanting, Mötley Crüe, Mötley Crüe. And they're like, why did they get our name wrong, dude? And it's like, no, they're getting your name right. You got your name wrong. Now, Francois, the archaeologist, went to the Motley Crue concert. What language is this written in? Because this is English, right? You'd see this in an English newspaper. But there are these characters here which are not part of the Latin alphabet that English speakers use. We got the sadir, we got the A, we got the O, and the U. Now, most of the time, what English speakers do is they just ignore the extra bits. Because we've never seen them, we don't know what they mean, we don't know if they're important, and we can't cope with them, so we just pretend they're not there. But different countries have different conventions. This is my friend Magnus. He's a Microsoft cloud architect, Azure consultant based out of Malmö in Sweden. And his name is not Magnus Martinsson. Lots of English people think it is. His name is Magnus Mortensson, because the O there, that's a letter of the Swedish alphabet. And so a couple of years ago, Magnus is going to Microsoft in Seattle, and he's crossing the border. He's got a Swedish passport. And at the bottom of your passport, you have these two lines here, which have to be machine readable. And when they say machine readable, they mean readable by 1960s American mainframes. Got to be basic 7-bit ASCII. Now, the Swedish government has a rule that says if you have the letter O, you replace it with AA. So it comes out as Martensson, M-A-A-R. But the people who printed his airline ticket, they didn't get that memo. They just take the circle off because it can't be important. So Magnus tries to get into the United States, and he's got a passport and an airline ticket that don't exactly match. Now, I don't know if you know the kind of people who work at the airports in America. They're well-read, cosmopolitan, educated, Now, he's a well-dressed, educated, charismatic guy going from Sweden to visit Microsoft, and even he had to answer some questions about how this happened. You imagine the number of people every day traveling around the world who they have a name that made perfect sense when they were growing up for their family, their friends, and then it gets put into the bottom strip on their passport, and now somebody at the airport's given them a hard time because they're like, this doesn't match, and that person has no idea that any of this is even possible. We're just getting warmed up. Let's make a database of all the cities that we want to go to. So we've got Berlin, we've got Aachen in Germany, we've got Zurich in Switzerland, we've got Aarhus in Denmark, and Örebro in Sweden. And which one of these lists is in alphabetical order? Hands up if you think list 1 is in alphabetical order. Number 2? Number 3? Number 4? So even in this room, we can't agree what alphabetical order means. Very good. Because what we're going to do is we're going to put them in a database. So we're going to declare a table of cities, and then we're going to go here, and we're going to plug in insert Berlin, Aachen, Zurich, Aarhus, Örebro, and then we're going to say, all right, select star, there we go, we get our cities back. Right, let's find Örebro, which is what British people call it. Hang on, we put it. It was there a second ago, right? Maybe it's case sensitive. Maybe Örebro with a big O. No, still not there. Does Örebro equal Örebro? No. Unless we say, I want you to compare these strings using, this is a collation. This is the Latin general, case-insensitive, accent-insensitive collation. This is telling the database, think like an American, and tell me if these two pieces of text are the same, and it goes, yes. According to Latin General CIAI, they are the same. So now we're going to select order by name, all right? Now, to me, that makes sense, because I grew up with English, and so to me, Orebro is just a letter O with decorations, and the decorations aren't important. That's not how the rest of the world works. Latin General agrees with me, because that's a convention based on what makes sense to me. If we do the same thing with the Finnish and Swedish collation, Orebro moves to the end, because is the 29th letter of the Swedish alphabet. So they've got A through Z, same as English does, but then they've got a couple of extra letters on the end, and Örebro is one of those. If we do it with Danish and Norwegian, now does anybody think that list is in alphabetical order? But it's not. It's wrong. Because Aarhus is Denmark's second city, and the city of Aarhus was officially spelled Aarhus from 1948 until January 2011. What happened is, after World War II, there was a big government initiative in Denmark to change Danish orthography and spellings and words so they were closer to Sweden and further from German, which you can probably guess why. Like, they wanted to be with the neutral side, not the losing side. And so they had a Danish orthographic reform. And they changed the names of all kinds of people and places and businesses and towns, and they gave them this new letter at the end of the alphabet. So the town of Aarhus became Aarhus. But then in 2011, the people of Aarhus voted to change it back because Google wasn't finding it and they thought it was bad for tourism. And so they changed the spelling back again. But what that meant is it still stays at the end of the alphabet because it's a place in Scandinavia. So Aachen is in Germany. That goes at the beginning because AA is clearly at the start of the alphabet. But Aarhus, that's just a special way of writing or, that goes at the end. Now, this makes perfect sense. Any of you folks Danish? If you are, to Danes, they're like, yeah, that's obvious. I've done this talk in Copenhagen. They're like, that's obviously right. I'm like, how would the computer know? They're like, oh, yeah. Because there is not enough data in the text to get it right. If you have to build a system that is going to respect the rules of Danish orthography, you need two columns in your database because you need one that you're going to display, but you need a different one that you're going to use to sort it so you can get it right according to Danish and Norwegian orthography. And using that, you can put in an additional sort column, you get them at, and this is in what Danish people consider to be the correct alphabetical order. Now, a lot of people you talk to are like, yeah, I work in tech, but really, let's not bring politics into it. And you can't not bring politics into it because politics creates the problems and technology tries to solve them. And so if you want to understand why the files are in the wrong order on a Danish language version of Microsoft Windows, to really make sense of that, you've got to understand the spelling reform, and you've got to understand the orthography, and you've got to understand the context and the influence of the Swedish and the German alphabets on the way modern Danish has evolved. If you try to find any technology which has no politics in it, there's nothing there. Now let's go back to our friend Francois with his little C with a cedilla. Because one of the things that Unicode does is it says, well, we're not going to tell you how to do your job. We're going to give you enough tools that you can solve the problem, but then it's up to you, the engineers, to use the tools. So Unicode says, all right, you need this character. You can do this. We'll give you a code point for it. So Unicode plus OOC7 is C with a cedilla. Or you can use a regular C, like an ASCII-flavored C, and then you can draw this on it. And this is called a combining character. And a combining character is like decorations for whatever you just drew. And the wonderful thing about combining characters is you can add them. And you can stack them. And you go, I want a Z with a one of those, and a one of those, and a one of those, and a one of those. And just keep adding them up. And very occasionally, this will brick somebody's phone if you send them one of these. The Samsung Galaxy had a rendering bug that couldn't cope with this. But most of the time, you get Zalgo text. That's where this stuff comes from. And so we've got multiple ways of creating the same characters because we can use combinations. So if we've got the string Motley Crue, we could have Motley Crue, or we could have M-O combining diaeresis T-L-E-Y. Are these the same string? Well, we don't know. Why do you want to know? What are you looking for? Are they the same? Well, they have different numbers of bytes. We can see that. They look the same, they sound the same, they probably mean the same thing in this context. And again, what the Unicode does is it says, we're not going to tell you what's right or wrong, we're going to give you the tools. Normalization forms. It's a thing called the NFD, the Unicode canonical decomposition. It says, I want you to break the string out into the widest possible number of characters. And NFC is canonical composition. I want you to squash it down, combine everything. You've got combining characters, replace them with a single one, make it the smallest number of bytes. And then there's another mode which is called compatible. And they spelled compatible with a K because the C already got used for canonical and composition. And so what these actually mean, if we write a little bit of code like this, so we've got a comparison method here. This is in C#. And it's going to take those 4 different normalization forms. We're going to build 2 strings, and we're going to compare them binary, and we're going to compare them using all 4 different things. And then we're going to build the string motley crew by sticking characters together, and one of them is the Unicode 0308, the combining diaresis. And then when we .NET run this, what we get at the other side is they're the same string, they're the same length, they look the same, they're not equal, but they are considered equivalent under all 4 different kinds of normalization. Now, the other kind of normalization, compatible, is because Unicode includes things like bubble letters and fracture letters and fancy ways of writing letters that you can use in mathematics and formulae and physics. But it kind of knows that that still says plain text. It just says it in quite a fancy way. And that's what the compatible composition forms are for. Because if we now go in and we say, OK, .NET run that and compare it, we get 2 strings that are the same length. They're not equal. And under the canonical composition, canonical normalization, they are not equal. But if you use a compatible normalization that goes, yeah, well, they say the same thing. Like, it's not the same letters, but it is the same letters. And so if you've got one of the systems where people can put like little fancy letters in their username and then your search stops working, that's why. You need to switch the normalization use on it. Now, I mentioned like my journey with plain text. It starts when I'm 11 years old and I'm trying to print my homework and the pound sign won't come out of the printer because they don't use the same code page. The second big milestone in my career with plain text was I went into work a couple of years ago and somebody's like, dude, I think we've been hacked. And you get this all the time when you work in tech because people are like, they've accidentally right-clicked Facebook or something's happened. But the person saying this is like actually a very competent security engineer. They know what they're doing. They're not out to waste anyone's time. I say, why do you think we've been hacked? There's Chinese in the Windows event logs. And we go onto the Windows event viewer on our main database server. And sure enough, there is Chinese in the Windows event logs. And so incident management 101, right, your job. Check the firewalls, see if we've got any mysterious traffic overnight, look for Chinese IP addresses. Your job, database logs. See if you can find any evidence. Your job, I want you to search all the tables, see if this is like an injection attack. Can we find the text they've put in it? You tell the business we're investigating a potential breach, update for them in 15 minutes. I'm going to sit on my ass and I'm going to shitpost on Twitter, because that's management. And I solved it. Because I put this on and immediately got a reply back from a friend of mine going, that looks like a Unicode mapping error. And the fake Unicode account, which is wonderful, says, yeah, the low bits are all null, so this is probably UTF-16LE being mistaken for UTF-16BE. And I'm like, oh, I should probably learn what these things are, because it sounds like that might be important to solve this problem. So I dive like down the rabbit hole. I look up UTF-16LE, little endian, big endian. All right, what do you mean little and big end? Turns out that internally, like inside Microsoft Windows, almost all text is stored using 16 bits per character. It's a 16-bit encoding. Java does the same thing, .NET, JavaScript. It's very popular in memory internally. And what it means is that if you've got ASCII text, like the word delete, you've got a bunch of byte pairs here where one byte is null and then the other one has the value. And this is little endian or big endian, depends on which way round they are. And it turns out if you get them swapped around, ASCII teleports into the Unicode block that is used for Chinese. And so that's where the Chinese comes from, is its regular SQL statements having their bits flipped. Next question, what's flipping the bits? Why are we getting, what's going on here? It turns out that it wasn't being flipping. Now, a version of this talk that I did, someone emailed me, they put a YouTube comment up afterwards, and they said, do you want to know what it means? That one is dismembering the body of the livestock. That one's climbing. Now, when I saw this, I laughed out loud, because one of the people I was working with that day ran the message through Google Translate, and they came over and said, I think it might be malware. I think they want us to, kill a chicken and put, gemstones in its mouth. And I'm like, I don't think they want us to do that. But yeah, that's what the translation. And yeah, only one of these is still used in modern Chinese. The bits weren't getting flipped. What happened is that we had a faulty network switch in our hosting center, and every 3 minutes, it would just drop 1 byte, just vanish out of the stream, and so everything else would just get shunted sideways. And so for 3 minutes, we get Chinese in the event logs, and none of our queries would work, and the CRM was down, and the website didn't work. 3 minutes later, it would fix itself, because it would drop another byte. It took us 27 hours to figure out what was going on. It's one of the most memorable incidents of my entire career, and all because big endian, little endian. There are 2 different ways round, and neither of them wins. They both work as long as you know which one you're looking at. Now, for storage, for memory, for disk space, for stuff where it's all local and you want to go really, really fast, UTF-16 and 16-bit encodings work pretty well because it's neat knowing how long your strings are going to be because you know that every letter is going to take 2 bytes. When you get out onto the internet, and particularly the World Wide Web, it doesn't work so well. If we take a web page that is written in Ukrainian and it just says "Привет," just says hi, now these bits are Ukrainian Cyrillic. We need Unicode for those. The rest of it is HTML, which is based on 7-bit ASCII, and so all of these red characters, that's us using the internet to send null around the world, over and over and over and over again. 44% of this web page is just null, 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 over and over again, which is a tremendous waste of bandwidth. And so the UTF consortium came up with one of the most brilliant hacks in the history of technology. They came up with a thing called UTF-8. And the rule of UTF-8 is you've got a bunch of bytes. And if you have a byte that starts with a 0, that is 7-bit ASCII. Same as it's been since 1965. All of the old documents floating around Usenet and FTP and archives and everything, those are all UTF-8 without changing anything, which is ingenious. If you see a byte that starts with a 1, well, if it starts with a 1-0, you are in the middle of a multi-byte encoding sequence. You need to backtrack and backtrack until you get to a 1-1, and then if it's a 1-1-0, that is the beginning of a 2-byte encoding. If it's a 1-1-1-0, that's the start of a 3-byte encoding. If it's a 1-1-1-1-0, that's the start of a 4-byte encoding. And then you take the other bits, the bits in red, and that gives you the actual value of the character you need to go and look up. And this is brilliant, because this gives us loads of room to expand. Because it means that we can put in all the human languages. It means we can put in, when we make contact with the friendly aliens from Alpha Centauri, we can put all our alphabets in. And it means we can invent new alphabets and keep adding stuff to them, because we still do that. Because there is a new alphabet, which was invented within my lifetime that we've probably all used today, which is the emoji alphabet. Which might be an alphabet or it might not. Depends how you look at it. It started out as a set of 178 symbols created in Japan just before the turn of the millennium by a guy called Shigetaka Morita, who was doing iconography for Japanese mobile phones. They wanted like a data service for doing, when is your train here? What's the weather going to be like? And so they created this set of glyphs. Then 2008, Apple launched iPhone in Japan. Now, by this point, if your phone doesn't do emoji, no one in Japan is going to buy it, so they have to put emoji into iPhone. And everyone else around the world discovers that if you change your iPhone into Japanese, you can start sending all these cute little pictures, and they start asking questions. Like, hey, there's sushi here, but there's no tacos. Why is that? They got like a firefighter, and they've got an airline pilot, and they got this, but they all look like men. What's going on here? You know, I'm a woman, I fly a plane, where's my emoji? Now, at some point, Apple and Google, Android, got together, and they basically donated emoji to Unicode and went, it's your problem now, we don't want to touch it, and they ran away. One of the only times in history that Apple and Google have collaborated and then walked away from something. So now Unicode administers the standard for emoji. And the way they do it is kind of neat, because they incorporate all of these neat ideas. So we've got the thumbs up emoji, but then a few years ago, they said, well, why don't we use combining characters so we can do like thumbs up and things using different skin tones? And then they went, well, we can go a step further, and we can say, what if we take, we want a glyph here for a female astronaut. So we can take the Unicode for woman, and we can take a thing called a zwidge, zero-width joiner, and we can stick the lady to the rocket ship. And if your phone knows what that means, you get female astronaut, and if it doesn't, you get a lady next to a rocket ship, and you figure it out. And then they went, well, hang on, we could do that, and we could add the skin tone modifier, and so now we can have this whole range of different professions and ethnicities and identities and family groups, all using technology that was originally baked in long before emoji ever existed. Now, flags is really interesting. I'm from the Great Britain, or I'm from the United Kingdom of Great Britain and Northern Ireland. This is the flag of my country, and in Unicode, it is the regional indicator symbol letter GB, because it has an ISO country code. Now, the UK is a country as far as passports are concerned. It's not a country as far as football is concerned, because in football, England's a country. I told you it's complicated. ISO does not recognize England as a country. Even though we have a football team, they say, no, you're not a country. And so the flag of England is a hack. It's a black flag followed by the tag letters G, B, E, and G. Same system that's used for the flag of Scotland, the flag of Wales, and the flag of Texas, which is also in the Unicode set, despite the fact that it's not a recognized country. And then the pride flag is a white flag followed by a zeroth joiner followed by a rainbow. Now, this is where things start to get a little bit political because flags represent things. And some things are not popular in some countries. If anyone recognizes this. Anybody? Taiwan. Technically, the Republic of China. The country we all know is Taiwan. The official legal name of this country is the Republic of China, which is not the People's Republic of China, which is China. And this flag is illegal in the People's Republic of China because it is a symbol of Taiwanese independence. Now, if you have an iPhone and you go into your keyboard and you find the flag of Taiwan and you tap it out, you type a message, and then you go into your phone's region settings and you change it to China mainland, when you go back to your text message, the flag's disappeared. And it doesn't appear on the keyboard anymore. Because this is the concession that Apple made to be allowed to sell iPhone in China, was to say, we'll take out the Taiwanese flag. They won't be able to read it and they won't be able to type it, because clearly that's going to fix everything. I don't know. Now, Microsoft went a step further and they went, we're not getting into that. If you create a text file with a bunch of flag emoji in it, and you open it on Microsoft Windows, it doesn't draw the flags. It just gives you the regional. So like, okay, Kenya, Britain, Zimbabwe, Romania, Mozambique, all right, we get it. There are only 3 flags that are actually supported on the Windows operating system. They're the pride flag, the skull and crossbones, and the checkered flag that indicates you've just won the Formula 1 race. Now, I don't know if this is Microsoft saying that their official policy on Unicode is that gay pirates are winning, but it's certainly one way to read it, right? And the final chapter, like the last installment, the thing that really got me to dive deep into all this and start trying to pull it all apart and figure out how it works, was I went to Ukraine in 2017 to speak at the Build Stuff conference there. And it was my first time visiting any country that didn't use the Latin alphabet. And I'm just walking around, and I loved it. I had an amazing time there. It's a fantastic event. And I can't read anything. Like, I can't read the road signs. I can't read the menus. I can't read anything. But I can read the license plates on the cars. And I said to one of the folks I was visiting, I was like, why the Ukrainian license plates? Why are they in English? And they looked at me like, they're not in English. They're in Ukrainian. I'm like, I can read them. I can't read Ukrainian. So we're like, all right, let's figure out what's going on here. Now, there's a thing called the Vienna Convention on Road Traffic, which, coincidence, same year as ASCII, 1965, a whole bunch of countries signed this piece of paper saying, okay, if you want to drive your car from Poland to Bulgaria to Spain, it's important that our police can all read each other's license plates. So your license plate has to be in the Latin alphabet. And a whole bunch of countries signed that, including the Soviet Union, USSR. Now, in 1965, Soviet license plates looked like this. They had the full range of Cyrillic letters. And I'm imagining that there was a meeting somewhere where someone said, you know, comrade, we're signing the Vienna Convention. What if someone wants to drive their car out of the Soviet Union? And they went, you do not drive car out of Soviet Union. But if you could get special travel papers for road traffic, and they'd give you temporary plates at the border, and you'd bring them back. And so if you drove a Soviet-registered car out of the Soviet Union, you would do it on temporary license plates. Then in the 90s, when the Soviet Union was broke up into its member states, they all overhauled their traffic registration, and now they have license plates that look like they're written in English, in Latin, but they're not. Because the system they used in Ukraine is they took the Ukrainian Cyrillic alphabet, and they took the Latin alphabet, and they identified the set of characters that occur in both of them. And if you take that set of letters in English and you jumble it up, you get the phrase Pike Matchbox. Now, I want you to remember that, because next time somebody says to you, I'm going to send you a plain text file, you can say to them, do you know Pike Matchbox? And if they say, oh yeah, then they've seen this talk. And they know about big and little and Danish orthography and the spelling reform and Unicode and emoji and all that kind of stuff. And so they're going to send you a file that they've probably put some thought into it, and you're going to be able to open it. And if they say to you, no, what's Pike Matchbox? Then they're going to send you a file that works on their machine. Maybe it works on your machine, maybe not. We don't know, because there is no such thing as plain text. And I always like to dedicate this talk to a guy called John Doe, who watched the whole thing on YouTube for an hour and then left the comment at the end of it, leave politics out of software. Thank you. Thank you, Kraft.